Alright, welcome today to my General Control Techniques presentation. I'll be discussing Chapter 46, pages 567 through 592. The overview today, what we're going to be talking about is we're going to be talking about continuous batch processes, talk about the pros and cons of each of those, describe the common uses for split range control valves, talk about their usages. We'll explain the use of high and low selectors with controllers, limit controls, and how cascade control works. So instrument symbols, we use these a lot in our P&IDs and wiring diagrams. There's a bunch of standards with instrument symbols. They're used to represent the instruments and interconnections in our systems that we use. ISA, SAMA, and MCAA, they all have standards that you can find on the internet and can use. Two common types of processes are continuous batch processes. Continuous process is a type of processing operation in which continuous raw material is received and the resulting product is continually fed to the next operation. Batch process is when multiple feeds are received and the resulting product is fed all at once through the next operation in a batch. So continuous processes, good things about them, why they're mainly used, are multiple parallel operations can be installed so that individual units can be shut down without completely shutting off the full operation. So you have an assembly line or something like a process that you have and there's multiple different parts. The process can run by itself, even with one individual unit being shutting down. The whole process can still work through. This allows for saving of energy since not every part of the process has to start up. Usually with continuous processes, after it's started up, very little. It's not very common to have them ever shut off. You will have individual units be shut down for maintenance or whatever, but when talking about the full process, it does not shut off. It eliminates unnecessary steps, reduces processing time, and generally manufactures products faster and more efficiently. Labor costs are reduced, since after the initial startup, only maintenance is needed to maintain and monitor the system. The bad things about the continuous process is it's harder to adjust since the processes are a lot larger and since everything is continuously on. In order for you to make those big adjustments, you're going to have to shut off the whole entire thing. Scheduling maintenance is more difficult, just like I said earlier, with much relying on the system to function smoothly from an end. Broken or manufacturing part of the system could threaten to shut down production entirely. That's why you have to maintain these and watch over them, is because if something was to break and it wasn't caught almost immediately, you could have products that were completely messed up. Whether it's investment in machinery or engineers to get the system set up just right, usual costs to a continuous product system are often higher than batch systems. So whenever you're first installing these are going to be a lot more expensive than a batch process. But once you do get past that startup, it's going to cost less to maintain it than the batch. Speaking of batch processes pros, products can be produced in mass quantities, reducing overall costs per unit. Companies only focus on a small group of products, leading to a greater quality control and product expertise. Cost of labor is reduced as workers only focus on a particular task or set of tasks. Cost of machinery is reduced since one machine can handle several different product configurations. Since it's a lot smaller of a process, machines have to do are usually programmed and built to produce the different types of products that are being produced in those processes. Lends itself to repeat orders, meaning a smoother, more consistent product flow over time. It's easier to make the same thing multiple times than to continuously have to change and make different products. Machinery isn't always on, saving energy costs, since it does produce in a batch. It's not continuously having to stay on like the continuous one, where it only produces one unit at a time. Batch processes produce a group of units. Uh, so whenever it's not needed, it'll be shut down. So it saves energy. Uh, Bad things about batch is each batch must be tested for quality and uniformity before the future batches can be produced. So since everything is being produced in a batch, uh, every single one of those individual units have to be tested, and so that takes time. Machinery must be stopped and recalibrated between batches. So with the machines being stopped and recalibrated, what you have to do is, since it's not like continuous wear, you can shut something off and the process still goes. You shut this down, you shut the whole thing down. So that causes time. Storage costs are always high for large batches of the same product. Fewer varieties of jobs can be demotive for employees, since employees want to be important. They want to feel like an individual, and so with the batch process, it's harder to give those individual jobs to employees. Split range controls. Split range control is an application where two or more control valves operate using the same controller output signal range, with each variable using a portion of the controller output signal. The control signals can be split using IP transducers or valve positioners. So here we have a temperature controller outputting 4 to 20 milliamps, and it's controlling two different valves. One valve is going to be opening at 4 to 12, and the second at 12 to 20. So if it's somewhere in between the 4 to 12, that valve, the cooling valve, will either open and close depending on the amperage, and then once it goes past that 12 mark and goes closer to the 20 milliamps, the heating valve will open or close. Heating and cooling surfaces. So like we were talking about in the last example, these are mostly primarily used in heating and cooling applications. Heating control valves are easily selected to have fail closed. Cooling action will have fail open. The reason for this is so that one stays off while the other one stays on. You can't, it's not, it allows for, is to prevent anything from, it prevents them from both staying on at the same time, or for both of them to stay off at the same time. One of them is going to be constantly on, even with the fail open, fail closed. One of them is going to be on, while the other one stayed off. Split range control valves can also be used to establish the order in which control valves are operated, and thus the priority between different operations. So in this diagram we have a pressure controller controlling three different valves instead of two. The primary is going to be the vent valve, while the input signal is at 4 to 9.3 milliamps. So the gas is going to come in. Even if the controller is just barely on, it's going to turn on that valve. Whenever the amperage increases, is going to turn on the valve for user 2 to open, and then once it maxes at 14.7 in between 14.7 to 20 milliamps, it's going to open that user 1 valve. Throttling range increase is a method not commonly used. So it increases the flow control range of a control valve. Occasionally there's no need for a control system to handle a greater range of flow than it is possible to obtain from a single control valve. So two control valves calibrated to operate sequentially can be used to handle a greater range of flow. Drawback of this throttling is that it causes losses in precision and control. High and low selectors. High and low selectors receive multiple input signals at once and only passes the largest or the smallest signal to the output. So high sensors or high selectors, they get like a batch of signals and they pick out like the signal that's highest and outputs that. And low selectors do the same with the lowest signal. High selectors are usually used for temperature measurements. If you have like multiple sensors, and it's going to pick out the highest temperature sensor signal and use that as its output. Low selectors are usually used for level of tanks. Make sure that the transmitters don't mess up or the tanks go empty. Limit controls. Limit controls set the limits to signals high and low. So basically, if they both have a set point. With high limit devices, they compare the signal to a set point, and if the signal is lower than the set point, it'll pass it through. If it's higher, it will not allow it. It will just output the set point. Low limit devices will let the signal pass if it is higher than the set point, but anything that is lower than the set point will not get passed. It will just output the set point. Gap action works the opposite way than limit control does. Instead of measuring for a high set point or a low set point, it measures in between two set points. So if the signal is in between those two set points, it will allow it to go through. But if it's higher or lower than one of the two set points, if it's higher than the highest set point and it's lower than the low set point, it will not get passed through. Cascade control. Cascade control is a control strategy where a primary controller, which controls the ultimate measurement, adjusts the set point for a secondary controller. A secondary controller holds a less important measurement that influences control of the primary variable, which is displayed in the diagram below. That's it for me. There's my cited sources. If you have any questions, just post them in the comments below, and I'll be happy to answer them. Thank you, and have a good day.